afternoon.
Hello, everyone. Good afternoon, and we are excited to have you join us. I'm Rajesh Thallam. I'm a solutions architect at Google Cloud.
And I'm Skander Hannachi. I'm a solution manager with Google Cloud as well.
And we are part of Vertex AI applied engineering team with Google Cloud.
And today we're going to talk about how you can augment a Gemini-based Gen AI solution with open source models from Hugging Face. Specifically, we're going to talk about how to add time series forecasting model to a Gemini-based large language model.
So we go over today how to use Vertex AI platform to build out Gen AI applications, and we'll zoom in on a specific recent use case that our team has built to enhance retail and e-commerce product catalog metadata and content, and we augment with demand forecasting capabilities. And we do this with Google's new open source time series foundation model called TimesFM, which was launched on Hugging Face last week. And we walk through practical steps of integrating this TimesFM model into your Gen AI application.
So first, let's talk about the thought process and available options for building generative AI applications and business solutions with the Vertex AI platform. Vertex AI foundational model is a powerful multitask model that unlocks multiple use cases. However, when you're designing a Vertex AI, a Gemini-based solution on the Vertex AI platform, it can be a little bit daunting and overwhelming, the number of different design decisions you need to make. So questions like, should I fine-tune the model? Should I try to augment it? Use retrieval augmented generation? Which type of grounding method to use? Should I focus on a more task-specific model, or should I let kind of a really large multitask model handle everything? So one simple rule to keep in mind when designing these systems is that there is no one model to rule them all. There's always going to be scenarios where task-specific models or smaller models will do better. So essentially, it takes a garden. There is no one model to rule them all. And so that's where the integration between Vertex AI and Hugging Face comes into play. It allows you to bring in all the models you need into the Vertex AI platform and to choose those that are most suitable for your use cases.
So before we get into the stack, a quick distinction between our offerings. So we have Google AI Studio and Vertex AI Studio. So Google AI Studio is a prototyping tool for developers and data scientists to interact and test Gemini models and launch these applications very quickly and easily. And Vertex AI is an end-to-end machine learning platform on Google Cloud that offers tools to you for model training and deployment as well. And Vertex AI Studio has access to the same Gemini models that you have on Google AI Studio as well. And you can tune those models, distill Gemini models with your own data and augment them with extensions and grounding. And you can also include up-to-date information and take real-world actions with those extensions. And all of this gives you full data control and enterprise security and data governance and compliance that you need for your applications.
So I'm going to talk a little bit more about the Vertex AI platform now. So it's a unified platform to do both generative AI and predictive AI. It caters to a broad swath of users, whether a business analyst who just wants to dabble in predictive ML a little bit, all the way to a PhD level ML researcher who wants to write their own custom TensorFlow or JAX or PyTorch code, etc. Now, there's three components to the Vertex AI platform. At the bottom layer is the Vertex Model Garden, which provides you with it's essentially your repo of all of the different garden models available within the Vertex AI platform. And then on top of that is the Vertex Model Builder layer, which is where you take these models as building blocks, and then you fine-tune, you augment, you deploy, you add pipelining capabilities, etc., to build your own custom use cases. And then at the very top is the Vertex Agent Builder platform, where you can take out-of-the-box LLMs, etc., and configure them to build various agent-based use cases and various search-based use cases, and augment them with things like external grounding using the Google search, etc.
So on Model Garden, we have 130 plus curated foundation models across various modalities of tasks. You talk about text, dialogue, code, images, and embeddings for your downstream ML task. And you have choice and flexibility with Google to choose between Google first-party models or open source models or even third-party foundation models from our partners. And these come in various model sizes to match cost and efficacy needs that you may need for your Gen AI applications. And we also have the domain-specific models for security and healthcare. And beyond choice, you have built-in safety and governance that comes with a fully integrated platform. And we recently announced and launched integration of Hugging Face Hub with Vertex AI. So that means you can actually choose and deploy from thousands of foundation models on Hugging Face with a single click. And all this is without you managing any infrastructure or servers directly within secure Google Cloud environment. And today we'll actually show you one of those open models from Hugging Face and Vertex AI stack to build a generative AI application. So with that, I'll hand over to Skander to talk about the Gen AI application that we built.
Thanks, Rajesh. So we're going to focus on a concrete industry example of how to integrate an open source model with the Vertex AI platform and with a Gemini-based solution. Specifically, we're going to look at how we can add demand forecasting capabilities to a solution that our team has already built, which is using Vertex Gemini to augment and to enhance product catalog data in an e-commerce context. So, give you some business context first. So managing product catalogs in an e-commerce setting is one of the critical and most challenging things that many retailers, whether they're brick and mortar, whether they're e-commerce, whether they're third-party marketplace, managing these catalogs is a daily challenge that retailers have to face, and this includes adding new products, updating creating the listings for the products or updating the listings for the products, managing the metadata for the products in the back end, running periodic quality, catalog quality health and coverage health checks to ensure that search engines are able to find the relevant products because the coverage is accurate, etc. So our team in Vertex AI recently released a product cataloging and content enhancement solution that uses Vertex Gemini, the Vertex AI vector search engine, and Imagine to streamline and fully automate the process of generating the new product content and enhancing it. So from a user perspective, what the user journey looks like for this solution is first a merchant in a third-party marketplace platform, or a merchandising analyst if it's like a first-party merchandising solution, would upload a sparse, noisy description, like a brief, just one sentence or handwritten description of a product, along with an image of the product. Now, first it goes through a category detection module, which maps the product to the correct category, the correct class, the correct subclass. Now, once that categorization is done, then we've narrowed down the search space. We now identified which category the product's in. Now we go through what's called a filtering process to identify what are the detailed attributes of the product. So what is its brand, its colors, its size, if it's a fashion item, the flavors, the ingredients, etc., if it's a food item, etc. Now, finally, after those attributes are extracted, then we use Gemini to generate a detailed description of the product for use by the marketing team for putting on the front end of the website. And then we use that description and those attributes to edit the image so that we go from the basic raw image that was input. We have now detailed, more engaging variations of that same image in order to engage the users and make it more interesting for consumers. So from a system design perspective, what does this look like? And notice here that I'm using the word system design, which is kind of like standard software engineering jargon. But in today's world, this would be called a chain. I'm chaining API calls to LLMs, and I'm using like LangChain in the kind of modern jargon, so to speak. Well, not modern, like contemporary, so to speak, jargon. But looking at it from a system design perspective, what we have here is essentially what we would call a single path state machine. So each part of the user journey is a specific state, and then the user is in that state, they're performing that activity. There might be a human in the loop component where they would decide that they want to perform some sort of override on what was generated by the AI model first, and then they move on to the next state. Now, most of you know this already. There's a lot more to commerce and to retail than just simply listing new products. You want to review their performance, you want to forecast their demand, you're going to adjust their prices accordingly, you're going to make inventory plans based on that. And so let's see what would our system design now look like if we tried to add additional demand forecasting capabilities to it. Now, first thing you want to consider is that a merchant is going to the chances that they're going to be trying to forecast demand for products and listing new products simultaneously within the same kind of like task or the same activity is very low. Much more likely, they are going to focus on listing new products first. Once they're done with that task, then they're going to transition to another task. They might even like have different days of the week where they do one task or where they do another. So the first thing that's going to happen is we're going to have some sort of intent detection layer, which is going to figure out whether the merchant wants to perform like update new product listing and perform like product catalog health checks first, or are they interested in looking more at individual item performance and forecasting the demand, etc. So now we're in like what we would call agent territory. So we've kind of moved a little bit from like standard system design and into like true, contemporary AI, because like with the fact that we want to figure out whether the merchant is going down one path or the other, we're essentially building an agentic system that's kind of helping, acting as a sort of merchandising agent or a merchandising co-pilot. But before we get into there is one major challenge here, which is that demand forecasting is not an easy topic. I mean, demand forecasting, people have been doing this for decades now. Is it really that hard? Well, the math and the science is there. We've been doing demand forecasting for a while. That's what I did for a long time before I joined Google. But the problem is like the tools available historically for demand planning teams have been one of two types. Either out-of-the-box ERPs, which take a long time to set up, or custom ML pipelines, which also take a long time to set up, but the overhead and the complexities of setting that up can be somewhat different. So, like in Vertex AI, we have models like temporal fusion transformers or the Tide model. We have the BigQuery ARIMA, the BigQuery ML ARIMA Plus model. These are our advanced time series forecasting models, but they're kind of suitable for in-house demand planning teams, which have both the engineering resources and the processes that require that heavy-handed demand forecasting approach. This is out of reach for a lot of merchant personas. Now, that's where I said historically, because if you recall, at the beginning of the presentation, I said there is no one model to rule them all. It takes a garden. And that is where Google's just released open source time series foundational model. So it's a foundational model, but it's for time series, not for language, called TimesFM, comes into play. So TimesFM is a new model released by the Google research team in collaboration with Google Cloud. It leverages the same type of decoder-only architecture that Gemini, Gemma, similar large language models leverage, but it's trained entirely on time series. So it was trained on a large number of synthetic time series data. So we use our own expertise to figure out what are the typical time series profiles or the typical demand profiles, business time series, seasonalities and trends, etc., along with Google Trends data and with the Wikipedia page views data to generate a foundational model that has learned most of the time series patterns, and now it's pre-trained and is capable, just like a large language model, is capable of zero-shot learning various natural language tasks. This model is capable of zero-shot learning various time series forecasting tasks. So what does that look like? So here, if you look at the examples that we have, essentially zero-shot learning time series forecasting tasks, you have to think of it as similar to the way you prompt a model with a prompt. Here, you prompt the time series model with your available historical time series. So in the past, you used to have to train time series models to on the historical data set before you can forecast the future. Now you just prompt the foundational model. It's already been pre-trained on a very large number of time series. It's seen multiple examples already. And so you're prompting it with the historical sales, and it generates the forecast on the fly. If I may go back to the other slide, we have benchmarked TimesFM against multiple dedicated models that have already been trained on domain-specific data sets, and yet TimesFM, without any additional fine-tuning, just its pre-training, outperformed them in terms of accuracy. But much more importantly, for our use case here, TimesFM, what we're looking at isn't so much the accuracy. The accuracy is critical, obviously, but the accuracy plus the ability to generate forecasts on the fly without training. Because The previous models required long overnight batches to run on a daily basis in order to generate forecasts for the new SKUs, et cetera, things like that. Now we don't require that, and this is where this becomes critical for certain merchant personas who don't have the kind of the operational overhead or the bandwidth to use the older tools. It's the capability of generating the forecasts on the fly that really unlocks this use case for them. So now I'm going to pass it over to Rajesh to show you how we can build this solution in practice.
All right. Great. So let's see how we can integrate the TimesFM model on Hugging Face and deploy on Vertex AI. So going back to the user journey of the merchant in the product catalog solution, so here we will design and demonstrate the user journey to review the existing item performance by building an agent using the foundation models from Vertex AI and Hugging Face. Again, the goal is to show you how you can mix and match these foundation models, and you can build with different modalities so that you can unlock more interesting use cases and also product opportunities than a simple multi-turn or a single LLM-based agent. I know we mentioned agent a few times. So the way we define a generative AI agent is it's an application that has been deployed that attempts to complete a complex task or a user query by understanding their intent, the reason about it, and act on it by using tools to connect with the external systems or APIs. So let me explain what that means. So many of us believe that GenAI stack is just a simple call to an LLM, but generative AI models are very smart text generators. However, you may have probably realized that these models can have significant limitations as primitives. And that can make it very difficult to integrate these models into a broader application ecosystem. But to build these performant GenAI applications, and more specifically agents, you need a few more additional components. So we go from models to agents. So at this point, the agents are not just smart text generators. They actually analyze situations, use multiple tools, make informed decisions without constant human input. Like agents can handle multi-step tasks that LLMs cannot manage by itself. Like you may be researching a topic or troubleshooting code or maybe accessing a set of systems by chaining together multiple actions. So in most simple terms, an agent is comprised of 4 different components, like a model that can do tasks such as generate, summarize, or reason about it, and tools that can help the model to provide better responses, like by connecting to databases, APIs, or memory. And then orchestration, which actually glues and then brings all these components together. And finally, you need a runtime so you can actually productionize and deploy these deploy this at scale. So we jump into each of these momentarily. On Vertex AI, the way we have built the platform is you can take these pieces and break them down into primitives so that you can combine them as you see fit and give you more control. So you can actually plug and play each of these components as you need. So there are 4 key steps, and it all starts with the model. So you choose the flavor of model. You can fine-tune the model or evaluate the model for your own tasks. And today we'll focus on function calling, which is a native feature to Gemini models, which allows you to return structured data responses that we can use to call external systems or APIs. As I said, function calling is a built-in feature of Gemini API. So you can transform the natural language into a structured data and back again to natural language. This means there is nothing that you need to add on or install separately. It's just there for you to use it. Now let's see step by step how the function calling works. So step 1 is to define the functions. So basically, you're creating a toolbox of functions that Gemini model can choose from when you are giving a prompt. And each function has a name, description, input and output parameters, as well as the data types of each of these input arguments that you have. And once you have defined these functions, you need to wrap them in a tool. It's like a wrapper that can hold 1 or more dedicated functions or declared functions. And then it's time to call the Gemini model. And when you're making the call, you pass these tools as an argument where you're binding these tools with the model, which tells the Gemini model that which functions it should consider when selecting the best tool for your prompt. And there are some additional ways to connect Gemini model to the outside world. So you can add these layers on top of function calling to make these interactions with generative models more agent-like, scalable, and production-ready. So that's why we are excited to support LangChain on Vertex AI. So you can use our LangChain templates on top of function calling. So this can help you to turn your Python functions, as you're going to see in demo, into executable tools that the model can use to perform information retrieval or transactions via API calls. And when you add this higher level orchestration to get some agent-like behavior, you can implement your own custom logic with LangChain. So you don't have to rely only on the default templates. You can also customize them. And it's not just LangChain. You can also use Llama Index or your own orchestration frameworks as well. So you can use Gemini function calling and Gemini API on their own with no additional frameworks, or you can actually use it with your own favorite orchestration framework. So finally, when you're ready to productionize and scale the agent for business critical applications, you have to deploy these agent tools and orchestration layer on top of Vertex AI. And you can do this in a single command using our Vertex AI reasoning engine component. So what reasoning engine gives you the scalability, security, and reliability that you need to handle these agents for these most demanding workloads. And basically, with reasoning engine, you can encapsulate all these different tooling that you have as an agent that allows the other developers to build on top of this particular agent. So you don't have to worry about managing the prompts or chat history or orchestration frameworks. You can actually directly build on top of these, the agent itself. All right. So combining what we learned today about the models, functions, and reasoning engine, let's put this into implementation of the user journey that we have to review the existing item performance. So the way this works is from left to right, the system would take the user query, pass it to the Gemini model to understand the user intent, and detect the tools it needs to use to answer the query. So in this case, we're going to bind a couple of tools to the Gemini model. One which fetches the data from BigQuery, which is our serverless data warehouse for a given SKU. And the second function is to call the TimesFM foundation model, which will be deployed on Vertex AI endpoint, which can generate the forecast based on these historical sales that we get from BigQuery table. And the tools that are orchestrated is everything with LangChain on Vertex AI, and the agent will be deployed using reasoning engine as a remote service. So once this is deployed, we can actually make a very simple API calls to the remote service, which will be deployed, and the user's query would be sent out along with the models to connect to these different tools. All right, so let's build the demo. But before that, there are key 4 steps that we're going to see in the demo as well. So we start with deploying the TimesFM model from Hugging Face on Vertex AI prediction endpoint. Then we define the Python functions, which would act as tools to get data from BigQuery and then call the TimesFM model. And we'll define a LangChain agent and bind the model with these tools that we're defining in step 2. And finally, we'll deploy the agent on reasoning engine to access the agent as a remote service. All right, let's see this in action now. Cool. So it all starts with data preparation. So in the data preparation, we're going to download this data set from Kaggle, which has e-commerce sales data. So we download the data set. So we have specifically a sales report, which goes up to for about a few thousand SKUs for about 6 months of data that we got. And we push this data to cloud storage, and we create a BigQuery data set. As I was mentioning, BigQuery is our petabyte scale serverless data warehouse, which is built in with machine learning as well as generative AI models as well. And we load that data set that we download from Kaggle to BigQuery table. And then we are transforming this data set in BigQuery so that it actually works well with our time series forecasting model. So like, for example, here I'm doing some sort of a imputation for the missing days that we have in the data set. All right, so we load this table, and finally, let me scroll this down. So at the end, the data would look something like this. You have a date column, and you have a SKU, and the total sales for a particular day for that SKU, and then total inventory that's available in the planner right now. So once we have the data set ready, the next step is deploying TimesFM model from Hugging Face on Vertex AI endpoint. So as we mentioned earlier, so TimesFM model will be available on Model Garden, and you'll be able to do this with a single-click deploy, or you can actually use Vertex AI SDK. So today I'm going to be showing you how to deploy this using Vertex AI SDK. So we prepare the prediction environment by importing the libraries and then configuring the variables. Then we create the Docker repository. And next we download the TimesFM checkpoint from Hugging Face. And we push this downloaded checkpoints to cloud storage. And we create a custom predictor. So essentially, predictor is nothing but a handler which can take in the request and give you the response. So essentially, it loads the model artifacts into memory, pre-processes the inputs, makes those predictions, and then gives the response back. Again, once you have the Model Garden integration, you don't have to do any of these things. It would be pre-built, available pre-built within the container itself. And then we also have a HTTP server, which is built on Flask, which is going to just respond to the request and then gives you the response back. All right, so now we have this particular handlers ready, so we can run a few simple tests just to make sure the predictor works. And here you can see that the call that I'm making is I'm just initializing a TimesFM predictor, load the checkpoints, and then create the payload so that I can actually make those requests, and call .predict function of that predictor so it actually makes those responses and gives you the forecast, and do the post-processing on that. And these all, we are still running locally. We're going to build a custom container which is going to add all these dependencies that we have built. And we build the image, and we can run the container locally again just to make sure that things are all working before it's deployed onto Vertex AI. And you can use Vertex AI SDK to run this container locally. So the way to do this is we define a local model and get the container spec, and we deploy it to a local endpoint. So this is all still running locally on your notebook or wherever your IDE is. And we can just run some health check and then do the prediction on top of it. All right, so now all the local testing is all ready. Now we can push this particular model to model registry. So it's just, now we push the image and then call the model upload functionality with the local model and the model display name. The next step is to deploy to Vertex AI endpoint. So once you deploy to this endpoint deployment may take up to a few minutes, and then you can run the endpoint.predict, similar to what we have seen testing it locally. So the response from model is going to be something like point forecast and quantile forecast. So quantile forecasts are your 10% to 90% quantile that gives you the confidence interval of those particular forecasts that got generated. And now you can actually use this forecast as needed for depending on the SKU that we're going to be calling. So this is one of the tools that we have. Now the model is deployed on Vertex prediction endpoint. Now let's define the functions as tools, which will bind with model later, which is going to access BigQuery table that we have created and loaded the data set and then call the function endpoint. So this is exactly the same way that you define your regular Python functions. It's no different. The only caveat here is you need to have your descriptions for the functions as detailed as possible with the input arguments and the input data types so that model knows how to, when to use that particular function and also how to use that function. So I'm defining a few functions here to interact with BigQuery. The very first one is listing the data sets from BigQuery tables. Here I'm sort of hard coding it here. And then list the tables within BigQuery data set. And given a table, it's going to get the schema information, then run the SQL query on BigQuery, and then get the data set to work with. So essentially here, what we're doing is, imagine if you're giving a prompt and then you're asking the Gemini model to generate this SQL query, and that SQL query would be executed by these functions as the tools. All right, here I'm just running a few things to test it out locally to see if the functions are working correctly or not. All right, so the next step is to define the function to get the forecast from using TimesFM model on Vertex AI. So here I have a couple of functions, one which prepares the payload, and the other one is actually running the forecast. Again, as you see here, we have a pretty descriptive information about what that function does, and what are the input arguments, and then what exactly the function returns, and what is the data type of the object that is getting returned by this particular function. So we call the Vertex prediction and define the prediction endpoint, and prepare the TimesFM payload, and call the predict function by invoking the endpoint. Then once we have a forecast, then we can actually generate both the point forecast and quantile forecast as the response back. Just in case if the function is not able to respond back, then it's going to just return out an error saying that it failed to generate forecast just as a fallback mechanism. All right, so we'll just run a few tests and then plot those forecasts. So here I'm just querying our BigQuery dataset directly. So I'm getting the time series as the context. I want to send it to the TimesFM model. And here I'm calling the run forecast function that we have defined previously, and then I have the point forecast and quantile forecast. And because we have the data set for about 6 months, so we just use only the test data, and then we have a way to validate between the actuals and the forecasted values. So that's what I'm getting the actual time series context here, so that I can compare. And I'm defining a function here that just plots both the historical sales and forecasted sales along with actual sales. So here's a plot, basically the one which is on the left, this is all the one in blue is the time series context, and the green one is the actuals, and the dotted lines are the forecasted estimates that we got from the TimesFM model. All right, so now we have the tools ready. Now we have the data set as well ready. Now we have to define the agent, and we're going to bind these models and tools. So the way this works is you can define an agent using our default LangChain template that comes with Vertex AI reasoning engine. So here we are defining the model as Gemini 1.0 Pro. You could also use Gemini 1.5 Pro as well. And we're going to use the LangChain agent template. So we have define the model, and we define the model arguments that we want to pass, like temperature settings or any other model settings that you want to pass. And we're going to bind all these tools that we have defined before as Python functions. And we have the agent executor args. So these executor keyword arguments are to make sure you can return the verbose logging if you need it, and also return the intermediate steps as a chat history back to the model so it can actually assess the current state better. And we set up that agent, and I have a prompt prefix as well. Because the data set I have is the older data set, which is 2022 data set. So I'm just reminding the model that the current day is May 12, 2022, so that when it actually performs those BigQuery, generates those SQL queries, it's generating with the right data set. All right, so we define the agent. We can actually run this particular agent locally. So I'm defining a SKU, and then I'm asking the agent to query for what are the daily sales for SKU for the last 20 days and give it by date. Because I have enabled this with verbose on, so it actually shows me each and every step. Like it's calling the list dataset function first to find out what dataset in BigQuery it has to find out the tables, and list down all the tables that are present in that schema. And it also derived that what table would be the right to fetch for that particular query. Remember, it's for daily sales forecast for a given SKU. And it runs that SQL query, and then because I reminded that the current date is 2022, it fetches the right date as well. Because I asked for last 2 weeks, it's going to take that from that particular date. And because it's going to pass as a time series context, it's also ordering by the date as well. And then finally, you can see that basically because I asked it to get along with the date, it's printing out the date and total sales as a table. All right. So let's see what's happening behind the scenes when we execute that agent. The query request is getting passed to as a prompt to Gemini, and Gemini is going to reason about it and to find out like what tools it has to call and what is the right function that it has to call, and call those specific tools, and then reason about it, and then go this as a loop, and finally generate the response back. Again, we have a very detailed reference here that you can go through if you are interested to know what exactly is happening behind the scenes on the reasoning engine. Now the next one is, next query is basically, now we queried from BigQuery. Now I wanted to actually go and generate these daily sales forecasts for the same SKU for using the last 2 weeks of sales data that it has. So it follows the same steps. It figures out the tables that it needs to query, queries the data set as well, and fetches all the time series data that it needs to send it to the TimesFM model. And then finally, it calls the run time series forecast and generates the total sales forecast as well. All right, so now we have tested this particular thing with locally using default LangChain template. But as I was mentioning, so in case if you want to add more to the default LangChain template where you may want to include your own orchestration logic or business logic that you want to add, you can do that using our custom LangChain template. It's pretty easy to set it up. All you need is basically defining a custom LangChain agent with a setup function. And here I'm actually just adding an LangChain output parser so that I can actually parse the output better and do additional exception handling in this particular case, and binding the same tools that were defined before, and setting up, like in this case, I wanted to customize even the prompt that I'm using. So I'm downloading a particular prompt called super agent from LangChain Hub so that I can customize my prompt that I'm sending to it. So once I have defined like all those prompts, I can bind the model and tools to the agent, and also define a query function, which is basically invoke the agent executor. All right, so again, the steps are same. So you just basically call the agent setup and then agent query. Cool, so now we have defined the agent. We tested it locally. Now it's time to deploy this agent onto reasoning engine onto cloud. So we're going to do this using reasoning engine Vertex AI. So we define the agent again just to make sure that it has not really messed up during our testing in the previous call. So we redefine that agent. And here, reasoning engine.create. So here is where we're going to make the call with the actual agent model that we have defined, along with the dependencies that it needs to call this particular agent. Like it needs to access Google BigQuery in our case, and then Vertex AI SDK as well. So we just define all our dependencies along with defining the agent. So once we have this agent created, the next step is to, it basically takes a few minutes to deploy it on the backend. It's Cloud Run, so that's where it gets deployed. And then you can test the remote agent. So here again, I'm using the same prompt prefix, and I'm calling the remote agent.query. And just for the sake of it, I'm just asking like which tables that it has access to query from the BigQuery dataset. And it actually tells it, okay, I have access to these 3 tables here. And then coming back to the query, like what are the daily sales for the SKU that we have tried out before? So it again goes back and then traces that, okay, it goes and queries the BigQuery table, fetches it and formats it as a table, and then displays it along with the dates here. We can also ask like another query like generating daily sales forecast for the SKU. Again, the same thing that we have tested locally, we can do it with the remote service as well. Now we can actually share this agent with different developers, and they can also build on top of this agent, so that way they don't have to create these functions additionally, but if they want to add on top of this additional functionality, they can add as well. All right. So here you can see that it's running run forecast with those specific time series event context that fetch from BigQuery, and then gives you, as a table that again could be used for plugging into the GenAI application and then do something on top of it. So typically this is the backend flow. The way to integrate this into your GenAI applications is to call this particular agent in your web UI or anywhere that you're actually plugging this in. All right, so going back to the slides, Skander.
So the first thing that you want to take away from our talk today is there is no single foundational model to rule them all. There's always going to be task-specific models, smaller models that will come in useful and handy to augment any Gemini-based use cases that you build using Vertex AI. The second thing is that you can easily deploy all sorts of models from Hugging Face directly to Vertex AI using the integration through the Model Garden, just as we showed you today with the TimesFM time series foundational model.
The third one is how you can combine generative AI and predictive models that can unlock GenAI solutions' full potential. So as we have seen, we have combined the generative AI Gemini models with time series foundation models. So we can actually build those applications pretty easily on reasoning engine. And finally, when you are building these scalable GenAI agents, you can deploy it with function calling and reasoning engine as you need. Again, as I mentioned, these are plug and play, so you can use the function calling separately from reasoning engine as well.
So thank you all for coming. And we will be outside if anybody wants additional information on this use case.